Hello there, ATS 571 students. Dr. Shragi here, and I am here to walk you today through the lecture 10 in this semester. We're getting close, actually, to the end of chapter 2. In fact, I'm actually kind of pleased to see that we're actually about a lecture or so ahead of where I was expecting to be at this time, which is good news. It's going to give us more time to talk about things later in the semester that will be more difficult concepts. Today we're going to be talking about the thermodynamic energy equations, and this relates back to the broad theme of this unit of material, this module, if you will. It's the, we're talking about conservation equations, the conservation of momentum, the conservation of mass, and the conservation of energy. In this case, these thermodynamic energy equations are going to be about conservation of energy. Honestly, a lot of the stuff in this module is just a review of the stuff that you learned back in ATS 510, which is physical meteorology. I think all of you have had that class. In some places, it's just different notation or a slightly different purpose to some of these equations. Let me give you an example of that. Back in ATS 510, we learned a form of the first law of thermodynamics. The form we learned was dq equals cv dt plus alpha, pd alpha. Here in that form of the equation, back then in 510, we learned that dq was the change in energy per unit mass. This was by diabatic processes, things like radiation and conduction and so on. CV was the specific heat at constant volume. I'm missing a slide here somehow. T was obviously temperature, P was obviously pressure, and that alpha was specific volume. That's 1 over density. And with a little bit of fussing, Holton and Hackham just work on it with a slightly different form. They present that same equation down there as CV dt dt plus P d alpha dt equals J. What the heck is all that stuff? Well, let me just sort of here show you this dt dt term here. All they did is they just took the time derivative of both sides. So like there's a temperature dt and there's a change in specific volume with respect to time. And then they also worked with J here. Instead of using dq, they're using a symbol J. I'm not sure why J. I've never seen that in any textbook except for theirs right here. But they're saying J is the rate of heating per unit mass by diabatic processes. Things like the air particle absorbing long-wave radiation, or the air particle warming by conduction with the surface, things like that. All right, so I mean, once you know that there's just a handful of small differences in how they notate it, it's not really all that strange of an equation here. And it's going to turn out that there's a lot of things we can do with this form of the first law, and we're going to see in this lecture here. So for example, we can start tying that together with a way of thinking about the thermodynamics of dry air. For example, let's start with this form here that we have of the first law of thermodynamics. P alpha equals rho t, RT. Okay, that's just like P equals rho RT, except we divide it through by rho. And since alpha is 1 over rho, that's no big deal. And let's take the derivative of that thing with respect to time. Now, that's going to be a product rule, right? We're going to have the first times the derivative of the second term plus the second term times the derivative of the first term. All of that on the left-hand side. And then we're going to be able to do the same kind of thing over there on the right-hand side. The first times the derivative of the second plus the second times the derivative of the first. Just the same kind of stuff that we would be doing anytime when we're talking about ideal gas law. Now, I mean, anytime we talk about a product rule. Now, one of these terms goes away, of course. There's no dr dt because that r is the gas constant. It's a constant, so there is no change in r with respect to t. So we can kind of simplify this a little bit and get rid of that term over there. And we got this stuff left. Okay, now, if we take that term and we think back to what we did when we were deriving a form of the first law of thermodynamics, namely this form of this equation right here, we could move this term over to this side, and then we would have P d alpha dt equals J minus CV dt dt. Okay, and then we could take this substitution right here and plug it in for this P d alpha dt term, and we would get this form down here at the bottom. So there's just a little algebra here and doing a little substitution. All right, so if we just had that form here, let me mark this up a little bit. So we have this form, And then all we did from the previous slide, and then all we're going to do is do a little rearranging here. We're going to move these two terms to the right-hand side, and that's how we're going to get this middle form right here. And then we're going to move forward here. Now, this is a nifty trick. There's a nifty law that comes to us from gas chemistry called Meyer's law. Meyer's law tells us that Cp equals Cv plus R for any gas. That works for any gas and works for any mixture of gases. There's actually all kinds of cool things that come to us from physical chemistry about Meyer's law and so on. But you can see we can do a little factoring here. Notice on this side of the equation here, we've got an R dt dt plus Cv dt dt. So we could factor out that temperature dt and we'd have R plus Cv. But by Meyer's law, we can see that Cv plus R is equal to Cp. So we just did a little substitution there. Cp becomes, of course, the specific heat of constant pressure. You can find that in the back of the textbook. You can find that in your physical meteorology textbook, whatever. And so once you have that rearranged that way, you have this really useful form of the first law of thermodynamics. So we have those two different forms. You might remember we did the same sort of thing with it in physical meteorology, where we had two different forms of the first law. All right. So now, like, for example, we could take that form right there, and we can divide through by T everywhere, and then we could do some more math, because, you know, you've got these d temperature, I'm sorry, let's be through here. We're going to divide through by temperature, and then, so we'll have, like, J over T equals and all kinds of stuff there, and then you do a bunch of stuff that you learn in calculus and so on, and you end up with a form of the first law of thermodynamics called the entropy form of the first law of thermodynamics. And that's this form over here in this dashed box right here, where, okay, I mean, I always forget that 1 over T dt, let's make this over here, 1 over x dx dt is the same as 1 over log of x, I'm sorry, the log of, let me try that again, 1 over x, let's do this here, 1 over x times dx is the same thing as d log x. And so we can make that substitution here. That's where they got all this stuff that's in here about this d log t dt and d log p dt and so on is equal to, and then it's the diabatic heating divided by temperature. That happens to be the time rate of change of S, where S is our entropy. Okay, this is how entropy is changing in this air parcel with respect to time. This is not physical meteorology. We're not going to get all bogged down here as to what we mean by entropy. But we can tell you that, for example, for a process that is air parcel that is undergoing purely adiabatic temperature changes, this little equation right here becomes the same thing, but the right-hand side is now equal to 0, because we are experiencing an isentropic temperature change. We're not increasing the entropy. We are simply changing well, it's an adiabatic process, okay? We're expanding the air parcel or compressing the air parcel or something like that. If we take that previous equation and we integrate it from a state where the pressure is P and the temperature is T to a new state where the pressure is going to be PS and the temperature is going to be theta, and then you got to do a bunch more math that sounds like a great homework set, it gives you this nifty form right here. That final temperature, theta, is equal to the original temperature, T, times a number raised to the R over C sub P power, and that number is the ratio of the final pressure over the original pressure. This is an important equation in atmospheric sciences. It's one of many different ways that we could write Poisson's equation. You might remember that we've had, probably in physical, we had 2 or 3 different forms of Poisson's equation. Poisson's equation is just different ways of talking about ways to get the temperatures and the pressures of an air parcel. To get the temperature of an air parcel at a new pressure when you know its temperature and pressure at some old pressure. Now, as we've written it here, though, we're going to be using it for a particular way. Of course, we're using it to define our potential temperature. Where am I going here? Hello there. There we go. I'm missing a slide somehow. Okay, so we're using this here as a way, though, to talk specifically about potential temperature, which is what this theta here is. And theta will be the temperature of an air parcel if it is moved dry adiabatically to a pressure of 1,000 millibars. So this PS in here, this PS is going to be 1,000 millibars, or 100,000 pascals, or whatever units you're using in for the other value of pressure. All right, so one thing you can do with the Poisson's equation is you can combine it with the ideal gas law and get the dry adiabatic lapse rate. That's kind of a fussy thing to mess with. So we're not going to do that derivation. It's a hard thing to talk about in this kind of format here. But the dry adiabatic lapse rate, gamma d, that's a big gamma in the subscript d, is going to be defined to be equal to, and then, like I said, if you do all this math, you find out that it is g over c sub p. G is a constant. It's the acceleration of gravity. C sub p is the specific heat of air. It's the specific heat of air at constant pressure, and it's just going to be our change in temperature with respect to height of an air parcel. Okay, this is just our dry adiabatic lapse rate. We did the whole derivation back in physical meteorology, actually. By the way, I wanted to draw your attention to, I have no idea why the Holton and Hackham used little d's here instead of big d's. It's got to just be a mistake. I mean, don't get me wrong, most textbook would have used big D there. I'm sorry, little d there, because it's the Lagrangian derivative. It is how we are moving an air parcel. But that surprises me because they typically use big D. There must be it's either a mistake or there actually is some interesting difference between this and the material derivative they normally use. All right, let's talk a little bit about how this applies to stability of the atmosphere. This is static stability. This is the kind of stability that you know all about already. This is the kind of stability in which an air parcel rises if it is warmer than its environment and sinks if it's colder than its environment. This is just one of a whole lot of different kinds of stability in the atmosphere. We're going to learn more, especially in the second semester, about like the stability of like what makes troughs and ridges grow, or whether cyclogenesis happens. Even in physical meteorology, you had several different kinds of stability that were about air parcels rising and sinking that weren't static stability. There's potential stability and so on. But we are here specifically talking about, at a very basic level, static stability of the Earth's atmosphere. Now, at any given time, you could measure the environmental lapse rate of the air as, and we're going to call it gamma. So this is going to be the measured environmental lapse rate. I mean, we're talking partial T, partial Z. Okay, it's actually minus that. But this is a measured thing. You're measuring the air at different heights above the atmosphere, above the surface. And the way we write our dry adiabatic lapse rate was gamma D. We, of course, I mean, even intro students learn that you can determine the static stability of the atmosphere by comparing those two values. If gamma is less than gamma D, this tells us that the potential temperature is increasing with respect to height in the layer. This is a situation in which the atmosphere is stable. How do you remember that? Well, an easy way to think about it would be, you know that the environmental lapse rate is negative when you're in a temperature inversion, and you know that temperature inversions are statically stable. So if your value of your environmental lapse rate, gamma, is less than gamma D, that means that this is a stable layer. Potential temperature is increasing with respect to height. Any air parcel that is displaced is going to be experiencing an acceleration, a buoyancy force that is pushing it back towards its original altitude. So like if an air parcel is displaced downward, it's going to be positively buoyant. It's going to be warmer and less dense than its environment. It's going to want to accelerate back up towards its original altitude. An air parcel is going to be negatively buoyant under these conditions if it is displaced upward. It'll be more dense than the parcels around it. It'll be wanting to sink back, accelerate it back down towards its original altitude. A good use of a word here is we would say that the layer of the atmosphere is stable or stably stratified under those conditions. And so actually, we could take an air parcel and just displace it from its original location, give it a little push here, and as we lift it upward, it's colder than its environment. It's experiencing an acceleration downward. When it gets to its original altitude, of course, it is no longer experiencing an acceleration, but because it's moving, it's actually going to continue to move below its original altitude. But here it's warmer than its environment. It's experiencing positive buoyancy, and you just get this sort of oscillation. I'm drawing it along this axis here. this axis might, for example, be time moving that way. I mean, your air parcel wouldn't necessarily have to be translating, to the east or something. As it did this, it could be up just standing in place, but oscillating vertically. This oscillation is going to be faster when the atmosphere is more stable because it'll be, as the air parcel rises, it's quickly becoming more dense than the environment around it, and vice versa. The oscillation is slower when the atmosphere is closer to being statically neutral. I apologize, I have something stuck in my throat today. The frequency of the oscillation, of course, is n. That's that so-called Brent-Väisälä frequency. You might remember that name from physical meteorology. And you get n from n squared equals, and then this stuff here. Now, I'll just remind you, that actually is slightly different than what the book has on page 55. We might do a homework problem or something just to figure out why that's a little bit different there. But, the funny thing about static stability, on a synoptic scale, the atmosphere is always stable. It's only very small areas that might be less stable, well, that might be statically neutral or even unstable. By the way, even in a thunderstorm environment, it's typically not unstable. It's just that it's less stable, okay? And then maybe it's unstable with respect to moist air or something like that. Any unstable regions are quickly stabilized by overturning. I mean, we're talking about, like in a boundary layer or something like that where, okay, by heating the ground strongly during the day, the sun has resulted in a thin layer near the surface that is absolutely unstable. You might remember that would be something like a radix layer. That's not going to happen on big synoptic scales or anything like that. One more thing I want to talk about before we move on to moist thermodynamics in the next lecture here is the so-called Boussinesq approximation. I got a good old Joseph Boussinesq picture right there. He was a French mathematician and so on, who was deriving equations for fluid motion, and he decided to make some interesting, he said under certain conditions you could make a certain approximation. Boussinesq said, for a lot of different kinds of flow, the vertical displacement is not really all that big. The flow is mostly horizontal. And as a consequence, if the vertical displacements are small, the changes in density are probably pretty small. I mean, the most of the changes in density that experience the atmosphere are because of vertical displacements. Yeah, there can be changes in density due to things like the air parcels warming diabatically. But that isn't going to happen all that much. Mostly, doing a scale analysis, Boussinesq said, for a lot of type of things, we can just say, let's say the flow doesn't have changes in density. And so Boussinesq said, you know what, under certain kinds of conditions, it's okay to say that the density is just a function of, it's a constant, rather. We'll use rho naught for that. We'll just say, this is the constant density for this flow along this streamline or whatever. And then there's a whole class of ways to start deriving equations that use this. For example, we can take those horizontal momentum equations and we can say, oh, remember, they pretty much were the same thing before, except for now we have a rho naught rather than a rho. Where is that a big deal? Because if we had a rho there, well, that's really just a way of saying, we'd have to mess around with ideal gas law in there. We'd have to figure out what rho is and how rho is changing. Oh my goodness, that's a big mess. Hey, instead, let's just plug in a constant, rho naught. If their flow is reasonably well approximated by the Boussinesq approximation, this could save a lot of math. Similarly, though, under this approximation, air can't change density. So, for example, from the last lecture where we were talking about continuity, now it turns out the fact that the air is incompressible. In other words, the three-dimensional divergence, like partial u, partial x, partial v, partial y, partial w, partial z, is now equal to 0, because there's no way to have changes in density. Well, that can be a big approximation, too. That can be very helpful. Now, in reality, the atmosphere is only so well approximated by the Boussinesq approximation, but there can be situations in which this works pretty well. Okay, I hope that this stuff about the dry thermodynamics wasn't really all that big of a deal. Hopefully, between physical meteorology and even intro and other classes you may have had, hopefully the physics of dry thermodynamics, things like potential temperature and first law of thermodynamics, are getting to be pretty familiar to you. You mainly had to worry about the changes in notation, and everything else was actually not that big of a deal. Next time, we're going to finish up Chapter 2 by reviewing moist thermodynamics. And again, you've had quite a few classes where you've learned about things like vapor pressure, mixing ratio, equivalent potential temperature, stuff like that. We're now just going to be applying those ideas and getting them reviewed and into the notation and the uses that we're going to have for them in a class like dynamics. Okay, that's all I have for you today. Please let me know if you have any questions. I know this went a little bit faster than we would have done it in class, but that's just the nature of there not being any way, for us to have questions and so on. Please let me know if you have any questions. This has been Dr. John Schrage.